We'll jump into our pump quick. And that should, let's see if that'll pull up okay. And Jill, what we'll do, like normal, we'll let you kind of be the monitor on.
Yep, it's good on my end.
Is it looking okay? All right.
Yep.
So we should see airflow and duct design module number 3 pop up. And we should be on our very first screen on the PowerPoint. Can you see that okay?
Yeah.
Okay. Yeah, I don't know why it was fuzzy on the video with, you know, the people and stuff. And Jill, what we'll do is normal. As I said, you know, we're going to be doing airflow and duct design module 3 and 4 today, and I'll let you be my monitor. So we'll kick off when you say so. We are recording at this point.
I say go ahead and go. We might have one other customer tuning in. I sent him the link again today, but otherwise, let's not keep these folks waiting. They were in on time. Okay,
that sounds real good. Well, good afternoon, everybody. We're going to be concluding our airflow and duct design class for this go round anyway. And we're going to be doing module number 3 and 4. And a little bit later on today, I'll go ahead and put this out on our YouTube training channel as an archive or as a video out on archive on the videos out there. And Jill can certainly give you the link for all of that, so you can go out and review this again as many times as you like. And we're going to be calling today's session Airflow and Duct Design Module 3 and 4, Session 10-20-2020. So it'll be today's date code. Because when you go out there on the YouTube training channel, you're going to find there's going to be lots of videos out there. We have over 20 out there, and some of them may be duplicated. You know, you may see another airflow class out there, but if you want to specifically know which one you're looking at, just look at the airflow and duct design in our example, module 3 and 4, and look for that session date code. So, so if we have more than one out there, more than one session out there, I will always date code it with the word session and then today's date. In our example 10-20-2020 will be the date code, so you can go out and look at it as much as you like. So let's go ahead and jump into our program. So today we're going to be continuing our lessons about airflow and basic duct design. And some of the typical things we're going to be talking about today are going to be building a typical duct system and supply and return. So this is going to give us the opportunity to actually build a duct system, just a typical 3-ton system. And we're going to be using factory airflow charts and external static pressure to find airflow for furnace products specifically in this module. And so this is going to be really, really important to understand that the airflow charts that we provide from the factory on all of our air moving equipment is a key tool for finding airflow and looking at static pressure. As a matter of fact, just a quick little story today. I was on the telephone today with a commercial with some commercial units. We actually have 5 units, and every single one of those units are suffering from a very, very poorly designed duct system. As a result, their external static pressure is way off the factory charts, and they're just having multiple issues. So this is very, very important that when we talk about airflow and duct design, I'm very passionate about airflow and duct design, that we have to provide the right size ductwork, both supply and return, and we have to fall within the ESP, or external static pressure, which we'll talk a little bit more later. We have to fall within that criteria of the factory airflow charts if we hope to have the equipment working as designed. So this is a very, very timely program in that regard. So at this time, let's go ahead and talk a little bit about duct design based on velocity recommendations as the main consideration. Now, Manual D is our don't offend anybody, but Manual D is kind of the Bible in the industry, if you will, concerning airflow. And so Manual D is what we follow whenever we design a duct system. It's the standard. ACCA Manual D is the standard for airflow and duct design in the residential world. And this is a direct quote from Manual D. There are 2 sizes associated with every duct section: the size that satisfies the airflow requirement and the size that satisfies the velocity limit. And the final design is always based on the larger of these 2 sizes, on the larger of these 2 sizes. So if you design a duct system and you use the static pressure method, which is method number 1, if you design that system based on static pressure, and you end up, say, with a 6-inch duct on a particular takeoff or a particular section of duct, and you go back and you find out that the velocity is exceeding the velocity in that section of duct that Manual D sets forth in their velocity tables, you're supposed to go to a larger size duct to meet the velocity requirement. And so there's two methods actually to design a duct system. The one method that's used a lot in our industry is what we call the friction loss method, also called the total loss method, where you take a look at the fan capability and then you build a system to use up all the capability of the fan as far as moving air. Another method is to use the velocity method to look at the speed of the air moving through the ductwork and size your ductwork according to the velocity method, or the speed of the air moving through that duct section. And actually, if you read this quote properly, you find out that you have to satisfy the velocity limit and pick the larger anyway. So the way we're going to design our duct system today is going to be on the velocity method, which is very, very simple, very straightforward method. And as long as we have a design criteria set forth, a velocity criteria set forth, we can always design a duct system, both residential and commercial, based on the velocity method. So we're going to go ahead and do that today. Now, it should be noted all duct runs and takeoffs are going to be equipped, or should be equipped, with a manual damper for final air balance. So one of the things about the velocity method that we always want to practice, good practice or best practice, is to make sure that we have a damper for balancing purposes. So once we put our ductwork in, we can then start balancing or making sure that each section of our conditioned space is getting the required airflow as per our load calculations. And so we'll go ahead and do that. So a couple of things that I want to stress: we're going to be building just a typical 3-ton duct system. So take out your air duct calculator, and we'll utilize the air duct calculator. I don't know if everybody can see me in the corner of their screen here, but that's with the little air duct calculator. So take your air duct calculator out, and we're going to start building a duct system based on the velocity method. Now, it should be noted there's going to be a couple criteria or base information that we want to keep in mind. Number one, we always want to design our duct systems to provide a total of 400 CFM per ton. So you see the little flashing text there to remind you, 400 CFM per ton. And so if we have a 3-ton unit sitting outside, this is 400 CFM per ton of cooling. Let me make sure everybody understands that. So if I have a 3-ton air conditioner outside, I need to provide 1,200 CFM in this, total CFM in this house or this space. If I have a 2-ton, I have to have 800 CFM, and so on. So 400 CFM per ton. So that's the first criteria I want everybody to kind of burn in their head. 400 CFM per ton is how we design our duct systems. The second thing I want to make sure everybody understands that before you build a duct system, you really need to know how much CFM is going to be required in each conditioned space, which is going to require a heat load calculation. Now, there's several methods that contractors have used over the years to determine CFM in a room, in each space, in each conditioned space. And the best way to do it is to look at the heat load on that room and then determine the CFM going in there by what we call a manual J heat load calculation. And so once we determine how much CFM we need in each space, we can then back into that and determine what size ductwork has to go into that space for a takeoff. So we're going to presume that that's all been done. And so we're going to start out with a supply trunk and an air handler or furnace. In our example here, just an air handler, and we're blowing air in a duct system. We're going to design a duct system on both the supply and the return based on Manual D recommendations and based on some of the things that are set forth as far as how much CFM in each space. So we're presuming we know how much CFM we want in each space or each room as we build this duct system. All right, so here's the exercise. When we build this duct, I'm going to give you one size of that duct. It's going to be a rectangular duct mostly on the main trunk. And then on the takeoffs going to each room or each space, it'll be like a round duct. And so you're going to use your air duct calculator. And I'm going to give you a criteria as far as velocity and CFM. Then you're going to use your air duct calculator to determine what size duct. All right, so excuse me again, got a little cough. All right, so we have a 3-ton unit. and we're moving 400 CFM per ton, so that means we need 1,200 CFM. So the first thing we need to do is we need to determine what size is our main trunk going to be coming right off of the air handling unit or the indoor unit. So please size all of your main trunk components, all your main trunk sizes, at 700 feet per minute velocity, 700 feet per minute velocity. 1,200, so that very first size of trunk, that very first piece of main trunk coming off of our air handler or furnace has got to carry the full 1,200 CFM because we haven't taken any air off yet to our conditioned spaces. So what I'm going to do, Tim, is I'm going to give you one side of that ductwork. And so in our example, we need 1,200 CFM. So take your air duct calculator and go to 1,200 CFM, and then line up the velocity of 700 feet per minute velocity. Now on your air duct calculator, that's going to be that little window on the right-hand side. Remember, we reviewed that last time, module 1 and 2. So I'm going to take 1,200 CFM, and I'm going to line up 700 feet a minute velocity. And that's going to give me a duct size. Now, if you look down below, I'm actually giving you one dimension of that rectangular duct. It's going to be a 14 by something on that first piece of trunk to give us 1,200 CFM at 700 feet a minute velocity. So as I line up my air duct calculator, velocity in feet per minute, 700. Air volume in CFM, 1,200 CFM, because it's a 3-ton unit, 400 CFM per ton. One side of my ductwork is 14 inches. What's the other side? So that's the exercise. That's the interactive part of it. So what's the other side? A 14 by what gives me a 14 by what for our main trunk for 1,200 CFM at 700 feet a minute velocity. Everybody find that? Okay, Jill, can you hear me okay? I'll have it, just anybody, if you'll please unmute your mic, make sure that we can, that we're streaming okay on the audio.
Yeah, I can hear you.
21.
Okay. All right. So as we do this interactive, go ahead and just unmute your mic, and if you've got the answer, go ahead and give me the answer, and then mute your mic back up, and then we'll make this kind of interactive. So a 14 by something will give us 1,200 CFM at 700 feet a minute velocity, feet per minute. What size duct would that be? I've got about a 14 by 19 off of my duct calculator, about a 14 by 19. I think I heard someone say like a 14 by 20. That's close. Okay, so that first section of duct is going to be about a 14 by 19. Maybe up to about a 14 by 20, something like that. And again, based on the air duct calculator you've got, ours, may read a little bit different than the other one. But if you're within a, 1 inch or so of the nominal, that's fine. So a 14 by 19. Now, on our takeoffs, our branch runs, in other words, remember, we're going to recommend a damper on each branch run. And we're going to have our branch run velocities at 600 feet a minute. And that's right off the velocity table that we discussed last week on when we were looking at our manual D velocity tables. So all of our branch runs we're going to size at 600 feet a minute, 600 feet per minute for our branch runs. And so remembering that at 600 feet a minute, our very first takeoff, we're going to have to provide 135 CFM into this first room. So we've done our manual J load calculation or other method of determining airflow into each space, and we need 135 CFM in this first space, but we're going to size that ductwork at 600 feet a minute velocity. So take your air duct calculator, and find 600 feet a minute velocity on the air duct calculator. And then we're going to go 135 CFM at 600 feet a minute velocity. And you're going to notice that's going to give us about a little over a 6-inch duct. Now, team, what I'm going to recommend that you do, if you fall in between, you know, on your round duct diameters over here, if you fall like in between a 6 and a 7, just round up to the next size is perfectly fine. That way, you know, you're not going to have any noise issues. But if it ends up being like a 6 point, you know, a 6 1/4 or something like that, it's okay to round down as well. So in this first space, we need 135 CFM. If you take your air duct calculator and line that up, you're going to see that at 600 feet a minute velocity and about 130 CFM, 135 CFM, you're going to need a little over a 6-inch duct. So a 6-inch will provide 100 feet a minute. Any questions or comments so far? Go ahead and unmute your mic if you have a question. Okay, well, as we continue doing takeoffs, let's go ahead and do another one. We have another takeoff at 150 CFM at 600 feet a minute velocity. So referring to your air duct calculator at 600 feet a minute velocity, line up 150 CFM air volume on your duct calculator and 600 feet a minute velocity for your velocity design point, and then go over and look and see that that gives us a little over a 6.5-inch round duct. So on this next example here, this 150 CFM, we should size our takeoff up to 7 inches, up to 7-inch round duct. Any questions or comments? Is everybody good? Okay, well, the last takeoff we're going to take off before we transition down is 145 CFM. It's kind of right in between 135 and 100. Take a look at that. So if you take a look at your air duct calculator, that looks like you're going to need about another 7-inch duct, a 7-inch round. So in our example here, we've done some takeoffs now, and we've taken off 135 CFM into one space, 150 CFM into another space, and 145 CFM into another space. So these 3 takeoffs are going to be 7-inch duct. You could get by with a 6-inch on the 135 CFM. But if I was installing this job, because I'm putting a damper on each takeoff anyway, I'd probably just use 7-inch duct on all of those takeoffs in this example. Any questions or comments on how we derived at what size ductwork to use based on a branch run velocity of 600 feet a minute and the amount of CFM required in each of the spaces we're indicating on our screen? Any questions or comments on that? All right, team. Well, I'll tell you what, take your calculator out, take your smartphone and go to your calculator function. And then let's take 135 CFM in the first space, 150 CFM in the second space, and 145 CFM, and then add those up and then subtract that amount of airflow from our original 1200 CFM that we started with, because now we're going to be transitioning down to another size ductwork to continue moving that air down the main trunk at 700 feet a minute velocity. So take your calculator and add up 135 plus 150 plus 145, and that gives us 430 CFM. So we've taken 430 CFM off of that main trunk. So subtract 430 CFM from our original 1200 that we started with, and that should give us 770 CFM that we have left over. Now, team, this is important that we understand why we put transitions in the main trunk. So we have 770 CFM left over after we took off those 3 takeoffs. We have 770 CFM left over. And what's happened is we need to speed that air back up to 700 feet a minute velocity for our main trunk velocity. So take your duct calculator, and we're going to go from a 14 by 19 main trunk, and we're going to transition down to another size main trunk to maintain that velocity down the main trunk. So we're going to go from a 14 by 19 down to a 14 by something to give us 700 feet a minute velocity in the main trunk at 770 CFM. So go ahead and take your duct calculator and find 770 CFM at 700 feet a minute velocity. We're going to see that our next duct size, we've gone from a 14 by 19 down to about a 14 by something to give us that main trunk velocity. Now remember, team, if you're within an inch or so, that's going to be close enough. So, you know, on my duct calculator, it looks like about a 14 by 13 or something like that. About a 14 by 13 will give us our 700 feet a minute velocity, and it will carry that 770 CFM down the next section of trunk. Any questions or comments how we arrived at that number? Is everybody good? All right, well, so our next section, our next main trunk section, to carry that 770 CFM down the next main piece of main trunk section, will require a 14 by 13 duct. So we've transitioned from 14 by 19 down to 14 by 13. And by the way, team, that's why we put a transition in the main trunk. It's because as we take air off of any main trunk section, the air starts slowing down as we take air out of that section. So we have to take that remaining air and continue to push it down the main trunk, but we want to squeeze it down and speed it back up to our main trunk target velocity in our example of 700 feet a minute velocity on our main trunk. So in this next section of duct, we've got 770 CFM at 700 feet a minute velocity. And now let's go ahead and start taking off some of our, some more takeoffs here for the next sections in our conditioned space. So in this next section here, we've got 90 CFM. Maybe it's going to a small room or, you know, maybe a large closet or something like that. So find 90 CFM. Now remember, team, we're going to be jumping down to 600 feet a minute velocity on our takeoffs or our branch runs. So let's find 90 CFM at 600 feet a minute velocity. And let's see what size ductwork we need. So it looks like on that example, we need about a little over a 5-inch duct. So if we're sizing our ductwork, our takeoffs according to velocity, which is the preferred method, at 90 CFM at 600 feet a minute velocity, it looks like we're going to need about a 5-inch duct, or, you know, you could go to 5.5-inch duct, but they don't make a 5.5-inch duct. So a 5-inch duct would be, a 5-inch round duct would be sufficient for that 90 CFM on that particular run. Any questions or comments on that? Is everybody good? Okay. The next 2 runs that we have on this duct are the same size, and they're 125 CFM. So referring to your air duct calculator, take 125 CFM at 600 feet a minute velocity. And we see we need, again, a 6-inch duct. So we'll have 6-inch takeoffs for those 2 125 CFM spaces. Now, team, go ahead and clear your calculator for me. And let's take 90 CFM plus 125 CFM plus another 125 CFM. And we find that we took off 340 CFM in that section of main trunk. So subtract that 740 from our 770 that we have in that trunk section. And that leaves us with 430 CFM left. So go ahead and do that for me on your calculator. Take 90 plus 125 plus 125 and subtract it from that 770 in that section of main trunk. And that should leave us with 440 CFM left over. So at this point, team, we're going to have to transition that main trunk down again to pick our velocity back up to 700 feet a minute velocity. So let's go ahead and take our calculator, and we're going to transition that main trunk down to where it's going to take that 430 CFM that we have left over and speed it back up to 700 feet a minute velocity to carry that air down to the end of the main trunk. So take your air duct calculator and find 700 feet a minute velocity. And then line it up with 430, or get real close to it. And we find we're going to need about a 13 by something duct. About a 13 by something to give us a main trunk size to speed that up to 700 feet a minute velocity. So if you look at your air duct calculator, it looks like about a 13 by 8. About a 13 by 8 will allow us to move that 430 CFM down the end of the main trunk at that 700 feet a minute velocity. Is everybody okay? And go ahead and unmute your mic if you would, please. Is everybody clear on why we have transitions and why we're trying to keep that main trunk velocity up to 700 feet a minute velocity so we can move that air all the way down the entire trunk section? That's why we have that. Any questions or comments on that? All right, well, this last section of main trunk, we've got 4 CFM left over, and we've transitioned the main trunk down to take that 430 CFM and speed it back up to 700 feet a minute velocity. And then we see that we've got 3 more takeoffs on this main trunk of about 140 to 145 CFM on those last 3 takeoffs. And that uses up the rest of the air on the trunk. So take 140 or 145 CFM on your air duct calculator at 600 feet a minute velocity for your branch takeoff or your branch runs. And let's see what size duct we need. So 140 CFM at 600 feet a minute velocity. If you line up your duct calculator, it looks like, again, about a 7-inch duct. It's actually 6.5, but we'll round up to 7-inch. So our last 3 takeoffs will be 7-inch duct with dampers on each takeoff on this duct system, team. That way we can balance the airflow when we're done. You'll also notice in the graphic that last takeoff that I did at 145 CFM, that very last takeoff on the main trunk at 145, I backed that up off the end of the main trunk and I capped the end of the main trunk. Does anybody know why I did that? Why would you not have that last takeoff at the very, very end of the trunk? What would happen if you did? Anybody?
It steals all your air.
That is an excellent answer. Yes, it depressurizes or steals all the air from the rest of the duct section. So good practice, good duct practice is your very last takeoff, back it up several feet if you can, a couple feet anyway. 18 inches is minimum is what we recommend. But back it up a couple feet if you can and have another section of trunk on the end and cap it off. And what that does, it keeps the pressure in the duct system. And to your good point, it keeps it from stealing the air from the rest of the duct section. So that's just good practice is to extend that main trunk out. A minimum of 18 inches is what we recommend, minimum, and then cap it off. And then what that'll do, that'll keep the duct system pressurized. Any good questions or comments on how we built this typical 3-ton system, utilizing the velocity method on the main trunk of a 700 feet a minute velocity. And we talked about velocities last week in our module 2 when we looked at our manual D velocity tables. And then our takeoffs at 600 feet a minute velocity on our branch runs. Any questions or comments on that?
What calculation are you using for your square footage to get you CFM per room?
That's a really good question. So are you asking about the CFM in each space, or are you asking for a CFM total on the house?
No, just your total per room.
Okay. All right. So basically, there's 3 different methods to find CFM on each run. A very old method was that contractors used 40 years ago when I got into the trade. They would figure 1 CFM per square foot inside of a room. So if I had a 10 by 10 room, about 100 square feet, then they'd need 100 CFM is how they did that. But then we started getting into buildings that had more glass load and higher ceilings and stuff like that. So the next level of figuring airflow in each space or each takeoff was to do what we call the cubic foot method. And so what we did there is we would calculate the square footage. In our example, a 10 by 10 room is 100 square feet. And then if it had a 8-foot ceiling, that would be 800 cubic feet. Okay. And then if we took that 800 cubic feet and multiplied it by our ASHRAE recommendations of 3 air changes per hour, this is called the air change per hour method, 3 air changes per hour for heating and 4 to 6 air changes per hour for cooling, then you would figure out the cubic foot area of that space, length times width tells how high is the ceiling, times the air changes per hour, and you'd come up with a CFM that way. And then finally, the last progression that the industry has really gone to is what we call a heat load calculation. So on the heat load calculation, if you take a look at your heat load calculation for each space, if you do a room by room heat load, that heat load calculation in that room will tell you the CFM that's required in that space. And so that's the best way to do it, is to do a heat load calculation. But if you really don't have any other way to do it, or you're not going to do a heat load calculation, I like the air change per hour method, which is you take a look at the square footage of the space and how high the ceiling is. And then I like to design 3 air changes per hour for heating and about 4 to 5 air changes per hour for cooling. And so you always size your ductwork for cooling. So let's just do an example real quick in our heads, just real quick. So let's say, for instance, I've got a 10 by 10 room with an 8-foot ceiling. I'm just making that up, okay? So it's 10 by 10, that's 100 square feet. With an 8-foot ceiling, that's 800 cubic feet inside that space. And let's say we're designing for 6 air changes per hour, 6 air changes per hour cooling. So 800 cubic feet inside that space times 6 air changes an hour gives us 4,800 cubic feet of air exchange per hour. But hang on a second. We don't do air changes per hour. We do CFM, feet per minute and all that. So if I take 4,800 cubic feet of air that's going to be exchanged per hour, divide it by 60 minutes in an hour, so that'd be 60 goes into 4,800. How many times? 8 times, right? 80 times to be specific. I'm just dropping some zeros in my little third brain cell. So that'd be 80 CFM in that example. So if you're not going to do the heat load calculation method, the cubic foot per minute, I mean the cubic feet method is a pretty good one. I use that for a lot of years. So you take the length times width times the ceiling height, multiply times 5 or 6 air changes per hour, divide by 60. That gives you the actual CFM for that space. Has everybody got that? Is that pretty well explained? Questions or comments? Okay. Well, team, if there's no further questions on the supply trunk sizing and how we could determine how much air we need in each space, let's go ahead and look at the return side. And so in our example, we're just going to have a main return trunk going back to our air handler or furnace. And that main trunk is going to have to carry the air back to the unit from our spaces, from all of our individual spaces. So we're going to size that main trunk going back for 1200 CFM. And we're going to look for a target return trunk size of about 600 feet a minute velocity. So if you take a look at our manual D velocity tables that we talked about last week, we see that that's well within the design criteria for the return trunk size. So if we take our air duct calculator, we can find out what size trunk we're going to need. So take 1200 CFM, because that return trunk has got to take all the CFM back. And a lot of times we find contractors keep that main trunk size about the same all the way. And so at 1200 CFM and 600 feet a minute velocity, we find we're going to have a main trunk size going back of about a 20-inch round. About a 20-inch round would be sufficient. Or if I'm building, or if I'm manufacturing or using rectangular duct, a 20-inch round rectangular duct would be equivalent to about a 15 by something. So about a 15 by 20 or 15 by 21 would give us a return trunk size going back sufficient for a 3-ton. Now, team, remember these velocity requirements. You'll find that in your manual D information in your handouts that, you know, if you've got the handouts for our program here. But that velocity table that we gave you in our handouts and we talked about last week on our PowerPoint, that's right out of manual D. And so if you'll follow those criteria, you'll never get in trouble with building a duct system based on the velocity method. Okay, any questions or comments on building a basic duct system, supply and return, before we start getting into static pressure and some methodology of measuring airflow with the static pressure method? Any questions or comments on that little exercise on building a duct system, you know, based on manual D velocity recommendations? Any questions or comments?
On that return, is it okay to go 14 by 20, or would you rather go 16 on that one?
That's a great question. I mean, so if a convenient size was more like if you could buy like a 14 by 20, if that was a convenient size, let's take a look at it. So if I had like a 14 by at 1200 CFM, that would give me a velocity of about 650. That would be acceptable, because I normally design a duct system, you know, towards the lower end of the velocity tables, but that would be acceptable. But you could also go a 16 by 20 if you went to a 16 by 20. If that would be a more convenient pre-manufactured size, that would give you a return velocity of about 550, and that would be perfectly acceptable too. Good question. Excellent question. What I would probably do on the return side, I like to have kind of large returns anyway, because it's nice and quiet. It gives you a real quiet system. So if I was in a situation where I either had to go up or down, I would probably go up to the 16 by 20 and slow that air down a little bit more, make it a nice, quiet, efficient system. Good. Excellent question. Any other good questions or comments? Okay. The next thing we're going to talk about is external static pressure, also called ESP. And ESP, external static pressure, is the total static in inches of water column that's going to be measured on the supply and the return duct of a system. And so if we think about it, the fan is really designed to move air through the duct system by providing a positive pressure, or a high pressure, a positive pressure on the supply side, and a negative or a sucking pressure on the return side. And so to find external static pressure, what we're going to do, we're going to measure the pressure on the supply side, which will be a positive pressure. And so we'll take a magnehelic gauge or a digital manometer, and we'll take our static pressure probes, and we'll poke a hole in the supply duct, we'll poke a hole in the return duct, and we'll take those static pressure readings, and then we'll add them up to get total static or external static. So what I like to do is I like to measure them individually, because then that helps me keep track of what side is giving me what pressure. So some technicians will take them together because maybe they have a meter or a gauge that allows them to take them at the same time to get an average between the two. But I don't like doing that. I like taking one pressure first and then take the other one and then add them up is what I recommend, because that gives you a nice clean break between the supply and return, and you know what the static pressures are individually on supply and return, and that's really a best practice, if you will. So step number 1, measure the supply side pressure and write it down to remember it. Step number 2, measure the return side pressure and write it down to remember it. Step number 3, you add them up, and then that gives you your total static, also called your ESP or external static pressure, or your total static pressure of the supply and return added together. So let's do some examples together. So if I'm on a piece of equipment, I've got a supply duct, I've got a return duct. And so what I'm going to do is I'm going to poke a hole in the supply, and I'm going to take my static pressure probe, and I'm going to measure the supply side static pressure, in the cooling mode or whatever mode I'm looking at to find airflow. If I want to find cooling airflow, I put it in the cooling mode, and I run it with all the panels on and everything so that I can read true static pressure with the air filter in place and all that, everything put together like it normally would be. I'm just going to poke a hole in the supply, put my static pressure probe in there, and then I'm going to do the same thing on the return, and I'm going to take the return side static pressure, and then I'm going to add those values together to find total, or what we call ESP, external static pressure, and total static pressure are the same thing. Now the gauge I'm going to use a gauge called a Magnehelic gauge, like we're featuring right here on the PowerPoint, or you can use a digital manometer. A digital manometer. Now team, this is really important. The old water manometers that you use for measuring gas pressure is not sufficient, is not accurate enough for these measurements. So you're going to have to get a Magnehelic gauge like what we're showing on our PowerPoint, which is a special gauge that's going to read fractional inches of water column, 0.2, 0.5, and so on, fractional inches of water column. Or you can get a digital manometer. Fieldpiece and Fluke and UEI, they all make them. And so you can get a digital manometer. It'll do the same thing, because we're going to be reading fractional inches of water column. So it has to be a very, very sensitive and accurate gauge. So what we're going to do, we're going to take our Magnehelic gauge and make sure that with it just setting in the room, it's at atmospheric pressure. Then we're going to take the high port on the Magnehelic gauge, and we're going to see it's going to deflect to the right-hand side of the gauge when I have a high pressure on there. So this particular gauge deflects to the right with a high pressure, and it deflects to the left with a low pressure. And so if I use that same port on there, it'll deflect one way or the other based on whether it's a high pressure or low pressure that I'm reading, return or supply, in other words. So we're going to feature the Magnehelic gauge today because it's easy to look at on the PowerPoint, but use whatever tool you have. Get a Magnehelic or get a digital manometer, but do not try to use the old YouTube water manometer for checking gas pressure. It's not accurate enough for this measurement. So what we're going to do, we take a look at those gauges. We take our external static pressure, is the supply side static. In this case, it'd be like a 0.50 supply. And the return static, which is, in this case, it swung the needle to the left. It looks like about a 0.2. And so if I add those values together, a 0.5 and a 0.2, that gives me a total external static of a 0.7 inches of water column. So it's just that simple. When we measure airflow, or we're looking at airflow, all of our factory airflow charts for both commercial and residential equipment is in static pressure. So if you take a look at the static pressure, you find the total static pressure, you look at the airflow chart from the factory, you can determine exactly how much airflow is moving through that cabinet at that point of measurement. So it's very, very easy to do, and we recommend, that whenever you commission a unit, or your troubleshooting unit, take that airflow so you know how much airflow you're moving across that coil and across those heat exchangers and so on. So we're going to do some examples together. Go ahead and you should have some handouts. If you've printed those handouts down, take your airflow chart for furnaces. Now remember, team, this is without a filter. And so you're going to have to account a little bit for the filter as well. But so this is your airflow chart for a furnace. Now this is how this chart works. If you'll pay attention to the PowerPoint for a second, this is how these charts work. On the left-hand side, you're going to find the model number of the product that you're looking at. So if it's a furnace, you're going to find this furnace model number. And then you're going to, that's step number one. So find out what furnace you're looking at. And then you're going to determine what speed tap the motor's on. So you're going to take a look at the motor and you're going to determine what speed tap it's on. You're then going to measure your supply and your return static pressure and add them up. And in our case here, we have a 0.5 inches of water column static pressure. That's our total static, 0.05. Now in our example, we had a TM9E furnace, 60,000 furnace, and we were on medium high speed tap. And if we move across the chart and we see at 0.5 inches of static pressure, the actual airflow that's moving through that furnace at that point of measurement is 1150 CFM. 1150 CFM. So again, just a quick review. Number one, determine the model number. What model furnace am I looking at? Number two, I determine what speed tap the motor's on. I physically, take the service panel off and I look in there and I see what speed tap it's on. I then start it up in cooling mode of operation. And I take my static pressure, my supply, and my return static pressure and add them together for a total, in our example, of a 0.5 inches of water column. I then come down the 0.5 column until I intersect the medium-high speed tap for that furnace. And then that tells me how much airflow I'm actually moving in that example. Any questions or comments on utilizing the furnace airflow chart before we do some examples together?
I have a question.
Sure.
I was always taught to go after the coil.
Okay, one more time. To go where?
After the filter and before the coil to get that static pressure.
Thank you for that great observation. On furnaces, you're absolutely correct. On furnaces, the coil's not included on this chart. And so you're going to go before the coil on a furnace and after the filter. You always want to go after the filter because that's going to give you how much suck that fan is pulling against that filter, correct?
Okay. Yes.
Yeah, and so you're absolutely correct. So as a little point or a little footnote on furnaces, the coil's not included on these furnace charts. Now it should be noted, maybe make a little note somewhere. A clean, most of our cased coils, if they're clean and and you've got proper velocity and airflow across it, but a clean coil typically has a static pressure drop of about 0.1 to maybe a 0.12 or something like that. So if the coil's clean and you got condensate running down it, it's the air conditioning mode, you're going to go ahead and add about a 0.1 to this number to give you more like about 1125 CFM, something like that, because you're going to pick up a little static pressure past that probe, so to speak, to your good point. So on furnaces, you go before the coil, and on both air handlers and furnaces, it's good practice to go after the filter so we know how much total suck that fan is pulling against that filter. That is correct. That was an excellent question. Any other good questions or comments? Okay, well, let's do some examples together, team. So referring to your furnace chart, you'll see that we're taking that static pressure before the coil on a furnace, just underneath the coil. And this is a TM9E 080 furnace. And that 12 MP indicates it's a 3-ton drive or 1200 CFM blower drive. So if you'll find the TM9E80 B12 furnace on your furnace chart, we're on the medium high speed tap. medium high speed tap. And our first static pressure reading is our supply static pressure. And it looks like we've got a 0.3. So a 0.3 static on the supply. So either write that down or remember it. And again, you can see the static pressure probe is underneath the coil or before the coil. To your good comment earlier. And so write that down or remember it, 0.3. Our second reading is after the filter, but before it enters the fan. And so we have a 0.5. So we're sucking against the filter as well. So we have 0.5 on the return. Now, team, what we're going to do to get our static, our total static, our external static, we're going to add that 0.3 plus 0.5. That gives us a total of a 0.8 inches of static, 0.8 inches. So referring to your furnace chart, that TM9E08012 MP furnace, medium high speed tap, what's the CFM? Go ahead, anybody unmute your mic. I don't have that chart in front of me. What's the CFM at 0.8 inches of static?
1097.
Okay, that is correct. Good. Give yourself a star. And so we see that by looking at static pressure, we can always extrapolate from the chart what our CFM is that we're moving through that piece of equipment. Good, excellent. All right, let's do another one together. So the second example is a TM9E40, TM9E40 A12, which is also a 3-ton drive. 12 means 1200 CFM up to 1200 CFM. We're on the high-speed tap on this TM9E40. High-speed tap. It looks, wow, it looks like we got quite a bit of pressure on that, quite a bit of static on that supply side. It looks like we've got a 0.6 on the supply, so either write that down or remember it. On the return, we have got looks like about a 0.95. So we've got some real issues with this duct system, don't we? As a matter of fact, if you take a look at your chart, a 0.6 plus a 0.95 is actually a 1.55, and our chart only goes up to about 1.0 product. And so at this point in time, we really have no idea what our real airflow is because our chart actually runs out at 660 CFM on high-speed tap on that furnace. So we know it's less than 660 CFM. We don't know how much less because our chart runs out. And so in this example, we see that we've got a 0.6 on supply and a 0.95 on return. So if I was going to remediate this duct system, if I was going to try to fix this duct system, the very first place I would start with would be the return because we've got a 0.95 on the return. And so that's another advantage, by the way, of taking these static pressures individually because it helps you determine which side has got the most static pressure. And so in our example, 0.6 was our first rating, supply. 0.95 was our second rating, return. And as I take a look at this, I see that I've got way high static pressure. My chart runs out at 660 CFM in this example, and I see that I've got 0.95 on return. So if I'm going to fix this duct system, the very first place I'm going to start is I'm going to put in more return. I'm going to establish or put in, make sure I've got a lot more return to get that return static down. And then once I do that, I can maybe even slow the speed down on the fan and maybe lower that supply static as well. But any questions or comments on this one? We've got a really bad duct system and the return's really bad. Any questions on that? Okay, that concludes, team, our airflow and duct design module number 3. Now, as we jump into module number 4, we're going to be doing more of this airflow stuff. We'll probably jump into some air handlers and things like that. But any questions or comments on our module number 3 as far as building a duct system, using a duct calculator, and measuring airflow on a furnace before we jump into module 4 as we start rounding out this afternoon of training? Any questions or comments? Well, team, I'll tell you what, then let's continue. And in this portion of the program, we're going to continue using factory airflow charts and external static pressure to find airflow for air handlers. So we're going to be looking at those air handler charts in this module. And then we're also going to talk about finding airflow using the old temperature rise method of airflow. So before this course is over, you will have had the opportunity to learn 3 different methods of airflow measurement. Number 1, the velocity method that we talked about last week with our rotating vane tool, our little whizzy wheel vane tool, rotating vane tool. We're learning today about external static pressure and how to use the factory airflow charts, which are, I like to use those a lot. As long as you've got your Magnehelic or digital manometer, you can use the factory airflow charts to get very, very close on the amount of air moving through that cabinet. But finally, we're going to also learn about using or finding airflow using what we call the temperature rise method, which has been around, for probably over 100 years. Basically, if you've got a thermometer and you can find airflow by looking at the temperature of the air going through the heat exchanger. And so there's a formula that we're going to plug in that we can show you, which we're going to share with you today, called the temperature rise method. It's a very old method of finding CFM, but I might add, it's an accurate method. So it was a way that we could measure airflow by looking at the temperature of the air entering a heat exchanger and the temperature leaving that heat exchanger, and then applying some math. And so we're going to talk about how to do that. It's very, very simple. As a matter of fact, there's been many times in the field where I've gone out on a field call with a contractor and they didn't have a Magnehelic gauge or they didn't have a digital manometer, but they had an accurate thermometer and they had an AM probe and they had some electrical tools and meters and stuff like that. And we were able to actually measure airflow by using the old temperature rise method. So we're going to teach you that method today as well, so that you can kind of have that in your tool bag as well. So let's go ahead and talk about airflow with air handlers, and we're going to utilize some air handler charts, just like we did with our furnaces in the last module. But the air handler charts are a little bit different, based on the air handler that you're looking at. You may have a particular voltage table that you have to consider. So, so looking at these air handlers, these happen to be AHR air handlers, which are just the old capacitor style air handler. And so the first thing we're going to do, we're going to determine the model number, just like we did before on the furnace chart. We're going to determine the model number of the air handler that we're looking at. And so once we determine that model, we'll then look at the voltage table, because on some air handlers, you have to consider the input voltage as a criteria for measuring your airflow. So if your air handler chart has a voltage table, make sure you measure that voltage on that air handler to see if you're close to the voltage on the table. If you're at 208 volt or the 230 volt table based on your line voltage on the job site. So number 1, again, you determine the model number of the air handler. Number 2, consider the voltage if you have a voltage table to look at on your air handler chart. Step number 3, you're going to determine the speed tap that motor's on, just like you did before. Look at the speed tap. And then you're going to correlate external static pressure with that speed tap to determine the airflow. So in this example, we have backing all the way up, we have an AHR 24B air handler, step number 1. And let's say we have 212 volts on the job site. Well, that's pretty close to 208, so we'll use the 208 volt table. In our example, we're on high speed tap. And I'm actually measuring an airflow or a static pressure of 0.50 with my Magnehelic gauge. Supply and return static pressure, 0.50 total. And I correlate that down, and so that air handler on high speed tap, 212 volt, in our example, 0.5 inches of static, is actually blowing 925 CFM through that air handler. Any questions or comments on how to use this chart before we do some examples together? Is everybody good? Okay, well, let's do some examples together. So referring to your air handler chart, now remember, team, be sure and look at the voltage table if we have a voltage table to consider on your air handler chart. So this is an AHR 30B air handler. So find AHR 30B on your handout. It's on the medium speed tap, but it's on the 200 volt table. Now remember, team, also this is important on air handlers. The coil is included on air handlers. Let me say that again. The coil's included on air handlers. So air handlers, what you're going to do, you're just going to poke a hole in the supply duct, and you're going to poke a hole in the return duct downstream from the filter, just like we did before. So we're getting maximum suck against the filter and the ductwork on the return side. Then on the supply side, just poke a hole in the supply plenum, because the coil is included on an air handler on the charts. So our first reading, AHR 30B, medium speed tap, 208 volt. Our first reading is a 0.3 on the supply. So please write that down or remember it, 0.3 on supply. And we've got a 0.2 on return. So please write that down or remember it. So a 0.3 on supply, 0.2 on return. We then add those values together for a total of a 0.5 inches of static. 0.5 inches of static, total static pressure in this example. Now, please refer to your chart at AHR 30B, medium speed tap, 208 volt table, 0.5 inches of static pressure total. ESP is 0.50 total. Somebody tell me, what's the CFM on this air handler, please? Okay, should be about 890 CFM, 890 CFM. All right. Jill, can you still hear me okay, just to make sure our audio's good?
Yep, I hear you. I just don't want any answers.
Okay, that's fine. I just wanted to make sure I wasn't rambling here. Okay, well, team, let's go ahead and do another one or two. On this one here, if you'll flip your page or go to your AE air handler charts, the AE air handler chart, you'll notice you're going to have a handout that says AE something, 18, 30, 36, whatever. So on the AE air handler, it's a little different. We don't have a voltage chart to deal with. This is the newer style air handler with a high efficiency motor. So if you take a look at the AE 18B, we're on high speed tap number 5. And our supply static pressure looks like it's about a 0.3 again. And our return static pressure on this one, like it's about a 0.2, so that's interesting. They happen to be the same static pressure readings as before. High speed tap. So as we add those together, our total static or external static is a 0.50 static pressure. So referring to your AE chart, 18B air handler, we're on the high speed tap number 5, a 0.5 inches of static. What is the CFM off of the chart, please? Anybody?
1023.
Okay, good, excellent. 1023. All right, let's do, I think we got 1 or 2 more examples just to make sure everybody's got this. So on this next example, we have an AE36C, which, by the way, that AE air handler is a very popular air handler we sell a lot of. High efficiency air handler. So it's a 36C. We're on the high speed tap number 5. And in our example, looks like we've got a 0.6 inches of static on supply. And about a 0.2 static on return. Our total static pressure in this example is 0.80. And again, you guys do what you want to do out there, but I like to take my static pressures separately so I can keep track of which numbers are for the supply and which are for the return. So in our example, we've got a 0.6 on supply and a 0.2 on return for a total of 0.80. And so on this particular job, it looks like we've got some pretty high static pressure on the supply side. So if I'm having issues with airflow delivery and noise and stuff like that, I would probably start on the supply side on this job because most of my static pressure is on the supply side. So what is the CFM at 0.80 total static on this AE air handler 36C on the high-speed tap? What's the airflow, please? Okay. It's less than 1348 because if you take a look at the chart, you'll see that the chart is actually going to run out at about a 0.7 on these air handlers. So we know that it's going to be less than where the chart runs out. Now, we don't know exactly what it is because the chart only goes up to like 0.7 on this particular air handler. Okay, any questions or comments before we get into the temperature rise method? The temperature rise method of airflow measurement as a quick review. Is there any questions or comments on the static pressure method that we use with our factory airflow charts and our ESP, our external static pressure, utilizing the factory charts? Any questions or comments on that before we continue with this review of airflow measurement with the temperature rise method? Is everybody good? All right, team. Well, listen, this airflow measurement using the temperature rise method is a very old method. It's been around, like I said, for a long time, and it says this. The temperature rise method says this: CFM, or cubic feet per minute, is equal to the output of the device in BTUs. And team, this could be a furnace. This could be an electric air handler. We'll probably use just an electric air handler because it's easy to convert to BTUs. But so if you can find the output in BTUs of any air handling device, whether it's a furnace, whether it's an air handler, whether it's a hydronic hot water coil, it doesn't matter. If you know the output in BTU of the heat exchanger or the device, and you divide that by 1.08 times the delta T of the supply and return air. So that delta T portion of the formula is the temperature difference between the supply and return air. And so to apply this formula, again, CFM is equal to the output of the device in BTUs divided by 1.08 times the delta T, or temperature difference between supply and return. Now, by the way, that 1.08 is a mathematical constant for standard air at sea level up to about 2,000 feet. That number changes very, very slightly at higher altitude. But for all practical field purposes, most anywhere in the United States, if you just remember that 1.08 is a mathematical constant for air, sensible heat rise on standard air, that's going to get you out of trouble. It's going to allow you to get real close with your CFM calculation. So the first thing we're going to do, if we have like a heat pump, we're going to energize the heat strips, and we're going to make sure that the outdoor unit is turned off. In other words, we don't want to have the compressor running. We don't want to have the outdoor unit running. And we're going to be selecting whatever speed tap on the motor that we want to check. But we're going to energize the heat strips and make certain the outdoor unit is off, and make sure we're on the airflow tap that we're testing. Step number 2, we're going to multiply the measured voltage times the amperage. So I'm going to take my amp probe and my voltmeter with the fan running on the desired speed tap that you want, and the outdoor unit's off and the heat strips are on. So we're going to be measuring the voltage and the amperage up to that air handler with the heat strips on, the motor running, outdoor units off, and I'm on the speed tap of the motor that I'm testing. And I'm going to multiply the voltage that I read on my voltmeter times the amperage times a mathematical constant of 3.414. And that mathematical constant, 3.414, is how we convert wattage into output. So volts times amps times 3.414 equals the output, or the BTU portion of the formula. We're then going to measure our supply and return air temperature. We want to do that within about 3 feet of the air handler, and then find the difference, or the delta T portion of the formula, of your supply and return error. So let's say our supply is 140 and our return is 70. The delta T would be the difference, which would be 70 degrees in that example. So we find the difference in temperature between supply and return. And then whatever that difference is, we multiply that number times 1.8 and then find the sum or find the number. Once we've got that number, we divide the output, the BTUs, by the result of step number 3 to find CFM. Now, team, it takes a lot longer to talk about it. It's very, very simple once you do it a timer. So let's do an example together. So let's say we're looking at a 2-ton unit. Let's say we have a heat pump, a 2-ton heat pump. We shut the outdoor unit off and we energize the heat strips and we turn the air handler on so it's blowing air across the heat strips, and we measure 249 volts. So go ahead and take your calculator and take 249 volts and multiply it times 33.6. That's the amperage that we're actually measuring on that air handler and the voltage on that air handler with it running, and the heat strips are on, and we're on the desired speed tap of the motor that we're testing, and the outdoor unit's off. So we have 249 volts times 33.6 amps. And once we have that information, we multiply that number, volts times amps, times 3.414. And that gives me a BTU output of 28,563 in our example. Now, team, go ahead and take that 28,563 and just write it down or remember it, because you're going to be dividing some numbers into that in a minute or two. So 28,563. Now what we're going to do, we're going to take our supply air temperature. We're going to measure the supply air temperature and the return air temperature. In our example, we have 105 degrees supply temp, 72 degree return temp. Now that's the delta T portion, so find the difference. So take 105 and subtract 72. And that should give you about 33. But we're not done yet. We take that 33, that's the delta T portion of the program, or of the formula, the delta T portion of the formula. So I take 33 times 1.08, and it's going to give me some number. So supply air temperature minus return air temperature times 1.08 in our example gives us like a 35.6. Now, to complete this formula, to find the CFM, I'm going to take that 28,563 and divide it by 35.6, and that will give us our CFM. So this method is very, very easy. Again, you know, a little bit of a formula. You have to plug in a little bit of math. So if I take on my calculator 28,563 divided by 35.6, what's the CFM? Anybody? Okay, I worked the math out and it was 802 CFM. So I've got a 2-ton unit and I'm designing my ductwork for 400 CFM per ton. And in our example, I've done the temperature rise method, and I see on my 2-ton unit, my ductwork is providing 802 CFM on a 2-ton unit. We're in good shape. Any questions or comments, team, on the subjects that we've talked about today as we kind of conclude our program today? And this session, or these modules, will be, we recorded this session today, and so we're going to go ahead and put it out there on our Champion Trainings, our YouTube training channel, and it'll be called Airflow and Duct Design Module 3 and 4, Session 10/20/2020. And so you can go out and you can review this as much as you like, go over it. It's a recorded session, you know, go through the formulas again or what have you. But before we conclude for the day, is there any final questions or comments on our training today before we conclude for today? Any questions or comments?
Joel, I'd just like to remind everyone that we have heat pump training coming up in November. If they're interested, just let me know.
Sounds good. Thank you, Jill. Well, team, I'll tell you what, if there's no further questions or comments, we're going to go ahead and conclude for this afternoon. I want to thank everybody very much for the opportunity to train with you today. And I know this virtual training is kind of different for everybody, but hopefully we'll be able to do some on-site face-to-face training sometime in the near future. But thank you again for your attendance, and please, by all means, look at the recorded sessions out there, and please be safe and please stay healthy. And one more time on behalf of your Johnson Controls champion team and our Wind Supply location who hosted us, thank you, Jill, and thanks for training with us today. Have a great day, everybody. Thank you.
Thank you.